YOLO11 is out, and in this tutorial, we'll fine-tune it for object detection on custom dataset. This guide provides a comprehensive step-by-step workthrough of the entire process, whether you already have your images or you need to find the data. No dataset, no problem. We'll start by finding 3 already annotated datasets for object detection. Already have images. I'll show you how to label them for training and create your dataset. Next, we'll train YOLO11 model. We'll cover training in 2 distinct environments, your local machine and Google Colab. Once we do it, we'll evaluate the trained model's performance and save it. Finally, we'll deploy the model, run it in browser, and use it with Python SDK. We have a lot to cover, so let's get started. Anytime that I need to train the model, but I don't have the dataset, the first place I look is RoboFlow Universe. There are already 500,000 datasets on the website, and most of them are for object detection. So there is a high chance that somebody already annotated the images that you or I need for training. And just scrolling through the website, we can see that those datasets come from different use cases. There is some football dataset, there are some medical images, some aerial images. There is dataset to detect fire and smoke. There are some datasets related to video games and datasets to detect safety equipment. And as a matter of fact, the dataset that I will use today in this tutorial also comes from RoboFlow Universe. So some time ago, I got interested in document understanding, and I was curious if I will find a dataset that will help me out to process ArcSIF papers. And that's how I found this TFT-ID dataset. And the cool thing is that you can go into those images, take a look at the annotations, evaluate the quality, and yeah, that dataset is exactly what I needed to make this tutorial. Like I said, many of you probably already have the images or plan to collect them. You may scrape the internet or take images with your phone or scan documents. And if that's the case, let me quickly show you how to annotate them. There are, of course, multiple options on the market, some of them open source like CVAT or my open source project called Make Sense. But if you're looking for something that is free to use and with minimum hassle, RoboFlow is probably your best option. And of course, I don't say that because it's RoboFlow YouTube channel. You can totally trust me on that. No, but honestly, I think it's the best. So let me show you how to use it. So for the next few minutes, I will pretend that I don't have the dataset that is fully annotated already, and I will use the subset of images from TFT-ID dataset to guide you through the whole labeling process. The first thing that you need to do is to log into your RoboFlow account or create one if you don't have one already. And once you do it, you will probably end up in this main workspace view. Here, I click the new project button that is in top right corner, and that takes me to project creation view. Now I can provide the project name. I'm just replicating the TFT-ID dataset, so that's the name that I'm going to use. And I need to provide annotation group. This is pretty much the answer to the question, what objects am I going to annotate? And in my case, those are going to be research papers. We select project type. Here, object detection, and create a public project. The first thing that you should do once you create a fresh project is define the list of classes that you would like to annotate. Like I said, I replicate TFT-ID dataset. So in my case, I will use figure, table, and text. Once you're happy with the list of classes, you can click Add Classes button. Success. Yay, great, successful. And now the next step is to upload your data to the project. To do that, we go to Upload Data view, and here we just drag and drop our images. And once we are happy with the list of images that you would like to add to your project, we click Save and Continue. Depending on the size of those images and the amount of images that you uploaded, that process can take between a few seconds and a few minutes. The next view allows us to pick the way that we are going to annotate the dataset. You can use the auto annotation functionalities that are in RoboFlow. But for this particular data set, I don't really recommend that. We can hire somebody to annotate the data for us, or we can manually annotate the data set. And this is the option that I'm going to use. Here, that view will probably look a little bit different for you. I have a lot of people in my workspace and I can just invite them to help me with annotation. But for this particular job, I will just assign those images to myself. And here it is. Our first annotation job is created and I can just start annotating. So I click Start Annotating button. This takes me to the editor where I can move between images. And let's say that I would like to annotate this one. I just zoom in. I draw the bounding box around the object that is interesting to me. I pick the class, I submit, and I just do it for every object visible on the image. So I had 2 more text fields, 1 more table over here, and 1 more text below that table. I try to make all the bounding boxes consistent, so the padding around the object is the same. Here is another page from a research paper, a large text field. Here's another text, and below it there is a small table, so just zoom into it to make sure that we annotate everything nicely. There it is, table, and here is another text. Let's pick the class. Great. I hope that you get the idea already. And once you annotate all of your images, you will end up in this approve reject view where you can, for the last time, take a look at all of your annotations, make sure that they are right before adding the images and the annotations to the dataset. I annotate all of those images myself, so I will just click add all, but you can be more granular and add or reject specific images. Once you do it, you can add your approved images to the dataset. This will take you to this view where you can select how many images would you like to put in your train, validation, and test subsets. I will just keep the default ratio of 70-20-10 and add those images. And the last step is to create the version. When you create the version, you can apply processing steps and augmentations. And for this specific dataset, I will skip the processing steps. I will even remove the resize, only keep the auto orient. And I will not apply any augmentations as I work with documents, so I don't want to flip them, rotate them, or I don't know, shear them. So I skip all of those, but for your specific use case, those might be useful. Click continue and create. And depending on the amount of images and their size, that creation step may take a little bit of time. But once it's completed, you finally have the dataset that you can use for training. And to do that, you will click the download dataset button, pick the export format that you would like to use. In our case, that will be YOLOv11, and download, but I will cover that step during the training process. We have the data. Now it's finally time to train the model. I will be using Linux machine with NVIDIA GPU, and I will perform most of the configuration and training using terminal interface. If you don't know Linux commands, don't be scared. I'll try to explain everything along the way and spell out what's happening. If you're using Windows, make sure to use WSL, Windows Subsystem for Linux. It just provides a more consistent and compatible environments for running all the tools and scripts. So here we are in Linux terminal, and the first thing that we are going to do is to create a separate directory for our tutorial. So I navigate to documents using a cd command, change directory. And once I'm inside, I create new directory called YOLO11 tutorial. And once again, I go into that directory. Inside, I create new VMs. And for those of you who don't know, VMs allow you to work on different Python projects in parallel. You can have different Python version in each venv. You can have different versions of your dependencies in each venv, and those versions don't clash with each other. And once I'm inside, I activate that venv. Now every Python related command that I'm going to run will be executed in context of that specific venv. Our Python environment is ready. Now it's time to fill it with all the necessary dependencies. To train YOLO11 model, you will need Ultralytics package, and one of its core dependencies is PyTorch. If you don't know, PyTorch is probably the biggest machine learning framework right now, used to research and deploy neural networks like YOLO11, for example. And to run efficiently, it's actually very close to your hardware. That means that you have different installations for CPU and for NVIDIA GPU and for AMD GPU. And to make sure that everything is configured properly, Ultralytics documentation actually recommends you install PyTorch separately on your own. And let me show you how to do it. The easiest thing you can do is to go to PyTorch.org website and scroll down a little bit. They have this really cool installation command generator where you can choose your operating system and the hardware that you are using, and the command changes dynamically depending on your configuration. I'm just picking CUDA 11.8, and I will tell you why in just a second. I copy the command and we go back to the terminal. So as you hopefully noticed, the structure of the installation command was depending on the CUDA version that I have installed. So let me show you how to check the CUDA version you have. There are multiple ways to do that. I will just use NVIDIA SMI or alternatively NVCC version. And my version of CUDA is 11.6. This is pretty old CUDA version. It's actually so old that in that command generator that was on PyTorch.org website, there was no command for CUDA 11.6. But the latest version that was there was 11.8, fairly close. So what I did is I copied the version for 11.8, and now we will do small edits to make sure that it will work for me. So I paste it in the terminal and I change the end number in the URL from 118 to 116, but probably already guessed it means 11.8 and 11.6. And I will do a few more edits. So I will remove Torch audio because we are not working with audio today, and I will remove the free at the end of pip free install because I can just use pip within my Python virtual environment. Now I click run, and yeah, depending on your internet connection, depending on the individual GPU that you have, execution of that particular command might take a little bit of time. So let's use the magic of cinema and skip the installation. Once the installation is completed, we can use pip list to list all the dependencies that are installed in our Python environment. And we can see that Torch and Torch Vision are both installed with support for CUDA 11.6, exactly what we need. And now we can just install Ultralytics pip package. So we type pip install Ultralytics, press enter, and here, just before, depending on your hardware, depending on your internet connection, the installation might take a little bit of time, but significantly less than PyTorch. Probably the largest dependency over here is OpenCV. But yeah, all around the installation of Ultralytics, once you have Torch already, Shouldn't take like more than 30 seconds. We see that it's already wrapping up. And yeah, once it's done, it's a good idea to run YOLO help just to confirm that the Ultralytics CLI works as expected. Looks like our Python environment is ready. Now it's time to download the dataset. As I said before, I'll be using this TFTID dataset that hopefully will allow me to train a model to detect text, figures, and tables in research papers. And to download it, I navigate to a dataset section, click download the dataset button, pick the export format that I want to use, in our case, YOLO11. And for the local training, I'll be using the zip file. So I check this radio button and click download. And depending on the size of your dataset, that might take a few minutes to complete. Once the download is completed, I'm back into the terminal, and the first thing that I will do is confirm that our zip file with our dataset is in downloads directory. And to do it, I will use ls command with two options, L and A. So I will use A option to print all the files, and I will use L option to do it in the long description format. And then I will look for files that have TFT string in their name. Remember, our dataset is called TFTID, and that's the grep command. And the pipe in between those commands is used to stream the output from the first command into the second command so that I can chain them. And indeed, there is a TFTID zip file in our downloads directory. So the next thing that I will do is I will create a datasets directory inside my current directory, so inside YOLO11 tutorials, and I will go into that directory. And then I will copy our TFTID dataset zip into my current directory. I can confirm that the copy operation was successful by just listing files in my current directory. Indeed, there is our zip file over there. Now I will use unzip command to extract files from that zip directory. And I will use, once again, two additional options. The first one is -q to make it quiet, because by default, unzip lists all the files that are extracted, and we have thousands of files. And another one is -d to specify the target directory. And now I will try to take a look inside the target directory to understand the structure of my dataset. And to do it, I will use the tree command. Tree command also has plenty of options, but first I will use -d, stands for directory. So this way, tree will only display directories inside directories. And once we execute that command, we can see that we have 3 subdirectories, train, test, and valid. Those, of course, stand for the dataset splits. And each of subdirectories have 2 more directories in them. So we have images and labels inside each subdirectory. And this is the structure of the data that you need to maintain for Ultralytics to understand how to load your dataset during the training. And to be honest, it's very similar to the structure of data that we know from the previous versions of YOLO model. Now, the next step is to go beyond directories and to understand the file structure. So another option that we can use in tree command is -L. That stands for layer of the tree. So we can decide how deep we want to go. And this time I am using -L3 so that I won't go inside images and labels subdirectories, because like I said before, we have thousands of files in those subdirectories. So those would just flat our terminal and we wouldn't be able to see anything. So we see 3 files inside TFTID dataset. There are 2 readmes that I don't really care about. and there is one data YAML file. And that file is certainly interesting to us, and I want to show it to you. But before I'll do it, let me just switch that -L3 into -L4 to show you the amount of data that we have in those directories. So we see that we have over 17K files inside the dataset, which is interesting, yeah, because we only had less than 9,000 images, but somehow we have 17,000 files inside the dataset. And I will explain why is that in just a second. But first, let's take a look at the data YAML file that I told you about a second ago. So to take a look inside files, we can use cat command. Cat pretty much prints the content of the file into the terminal. So I'm using cat and specifying the path of the data YAML file, and we can see that's pretty typical YAML file inside, not very long. So let's take a look, what do we have here? So first of all, we have train, val, and test keys in that YAML file, and those specify relative paths to the train, test, and valid subdirectories, or actually to directories storing images inside those subdirectories, to be precise, that I showed you just a second ago. Next, we have NC, that stands for number of classes, I believe. And in our dataset, we have only 3 classes. And the next one is names. And this is pretty much the list of the classes that we have in the datasets. Kind of redundant information. You don't need the NC if you have the names, but whatever. Okay, so now let's take a look at those files. Why do we have 17K files if we only have less than 9,000 images? So let me first list all the images inside the train subdirectory, or even better, let's just print the first 20 images. For that, we can use the head command, and we can just specify the number of entries that we would like to show. And because things are ordered alphabetically when you use ls, this order is constant. So we can just print the first 20 lines, and this is always be the same 20 lines. And once again, I'm using the pipe to stream the output of the first command into the second command. You know what? Let's drop the LA to make the representation a bit more concise. I'm only interested in the names. Awesome. And now we can open new terminal window. I will just move it over here. And here we will display the content of the labels directory from the train split. So just as before, I will only show you the first 20 files from that directory. And if we will take a deeper look, we'll notice that the names of the files in the images directory and the labels directory are the same. The only difference is the file extension. So in the images, we have JPEGs, and labels, we have TXT files. And you can see that the first file have the same name. If we will take a deeper look, the second and the third have the same name as well. And the last file also have the same name. So now let's copy one of those names. Let's go back to our original terminal and use cat once again, this time not to display the data YAML, but to display the content of that labels files. And once we do it, we see a bunch of numbers. What do they mean? Let me show you. Okay, so I went ahead and I copied the first 3 lines from our annotation file. If you would take a look at the original file, it had like 10 lines in it, but 3 lines is just enough for me to explain how YOLO annotation format works. And I also rounded all floating point numbers to second digit after the comma. For those of you who are unfamiliar with software engineering jargon, floating point numbers are just the numbers where we have some digits after the comma, and 2 digits is, once again, just enough for me to explain how the whole annotation format works. So in YOLO annotation, every line describes a single bounding box along with a class associated with that bounding box. So we have 4 floating point numbers that describe the position and the size of the bounding box, and we have 1 integer that describes the class ID of that particular bounding box. Now, those numbers in the txt file are separated by a single space, and they form kind of like this table. So the first column from the left is actually the class ID. Now, what is class ID? That's a convention that we use in computer vision. So for example, in our dataset, we have 3 classes: figure, table, and text. Those are the class names. But in practice, turns out it's often a lot more convenient to use number representation, not the text representation. That's why we map those class names into class IDs. Those are integers starting with 0 up to n-1, when n is the amount of classes that we have in our data set. So in our case, 0 maps to figure, 1 maps to table, 2 maps to text. So anytime that we'll see a line in our annotation txt file that starts with digit 2, that means that the whole line describes a bounding box associated with text class. Now we have 4 more columns starting from left to right. Those are x center, y center, width, and height of the bounding box. So it's a little bit weird that we use x center and y center to define the position of the bounding box, but this convention is coming back probably to the first YOLO model ever, and it just stayed the same through the years. Now, important thing is that those numbers are normalized. So x center, y center, width, and height of those bounding boxes that were initially expressed in pixels got divided by respective dimensions of the image, so that in the end the values are between 0 and 1. Now that we have our Python environment ready and we understand the structure of our dataset, it's time to start the training. You can do it in 2 ways, using Python SDK or the CLI, but for the purpose of this tutorial, I'll be using the CLI option. But before I trigger the actual training, let's run YOLO help command to understand the structure of the command we need to start the training. So we see that every command in Ultralytics CLI have this YOLO task mode and then additional argument structure. And if we go to Ultralytics documentation, we can see that values for the task may be detect, segment, classify, pose, and OBB. This stands for oriented bounding boxes. In our case, we are going to use detection. And the mode can be train, validate, predict, export, track, and benchmark. In our case, this is going to be train. If we scroll a little bit lower, we can see an example of a detection training command with some of those additional arguments specified. The most important of those are data. This is the path leading to data YAML file, the file that we saw just a few minutes ago. And model, this is the name of the checkpoint that we are going to use to start the training. There are also some additional hyperparameters that I will discuss in just a second. But before we do that, let's talk a little bit more about the checkpoint options that we have. So every task have 5 checkpoints that you can use, ranging from nano to X. And those checkpoints differ in sizes, so the amount of parameters the model have, but also the expected MAP value In that table, we can see values on Coco dataset. So YOLO11N have significantly lower expected MAP value than YOLO11X. And that's something that you should keep in mind when you will choose the checkpoint for your training. I'm using YOLO11N, but I'm only using that because I want to have small model so that it trains fast during the recording of the tutorial. In your case, you might actually aim for something bigger than the nano version. So now we are back in terminal and we can finally start the training. So what I do is I type in YOLO detect train command and I provide additional arguments. Like we saw, the first one should be data. And here I provide the path leading to data YAML that is inside the root directory of my dataset. The next one is model, and here, like I said, I will use YOLO11 nano version. I also specify two more hyperparameters, epochs, and set it to 5, and image size, and set it to 640. I will tell you more about those hyperparameters in just a second. I trigger the training, and it fails. And when we examine the error, we can see that Ultralytics CLI complains about incorrect path leading to validation images. And this is the error that a lot of people experience. So let me show you how to solve it. The first thing I do is I navigate to the root directory of my dataset. So go to Datasets, TFT-ID, and then I run pwd command. This is the Linux command that shows you the global path of the directory that you are in. And I just copy the result of that command. And we will edit the data YAML. I will do it using Nano. This is the command line editor, but you can use VS Code, pretty much any text editor that you have. And what I do is I update the paths to train, test, and validation subset. And I remove those two dots and I paste the result of pwd command. Essentially, what I do is I change the relative paths to global paths. Once I finish, I close, I save the file. I can confirm that the file was updated by just using cat data YAML command that we already know. We can see that paths to train, test, and valid subsets are now global. And now what we can do is we can go back and restart the training. So I just run the same command, hit enter, and the training starts. We see a lot of hyperparameters that either we defined or are set to default values. We can see the summary of the model architecture, and we see that the training runs. Now, what can we do to monitor our training? So let me go back to the second terminal window that we had open, and the most obvious thing is to run NVIDIA SMI. Here we see the GPU usage, but this is only the snapshot of the GPU usage that was registered at this specific moment in time. And if you would like that NVIDIA SMI command to be updated constantly, what we can do is we can use watch. This is the command that reruns the command all the time. And we set the update period to 1/10 of a second. This way we have this kind of like real-time training monitoring showing us the usage of our GPU. By the way, this NVIDIA SMI plus watch combo gives you very basic information about your training job. So if you would like to know more, there are other tools that you can use. Two names that come to my mind are NVTop and GPU Stat. So you can visit their GitHub pages, learn how to install them, and this way you will know a lot more about your training job, but also about the behavior of your model and the GPU memory allocation during the deployment. The model is training, so let me use this time to tell you a little bit more about those additional arguments that you can pass to training command. We only set 4 of them: model, data, epochs, and image size. You already know what model and data is, so let me tell you a little bit more about the rest of them, starting with epochs. A single epoch of training is model going through every image in your training set. So when we set our epochs to 5, that means that our model will see every image from our training set 5 times. The more epochs you set, the longer the training, but potentially the higher accuracy of the model you train. Image resolution is the resolution of the image used during the training, but also during the deployment of the model. So before the image goes through the model, it gets resized to some predefined resolution. This is because in your training set, there's a high chance that your images have different resolutions. So you'll resize all of them to a common resolution that you will use during the training. Now, if you set the image size to a higher value, you will have a higher chance to detect small objects, but the higher the image resolution, the higher the memory allocation your model will need to train. Another argument that have similar outcome is the batch size. So when I said that the epoch is a model going through every image in your training set, the model does not look at every image separately. It looks at multiple images all at once, and the batch size regulates the amount of memory, the images that model will see at once. So when we have 1,000 images in our training set and our epoch is set to 10, for example, the model will need 100 iterations to go through each image in the training set. But when the batch size is set, for example, to 50, it will only need 20 iterations to get through all of those images, in the end increasing the speed of the training, but also, like I said, increasing the memory allocation. Another interesting parameter that we see on that list is device. We can, for example, use this parameter to use multiple GPUs for training of a single model. I only have single GPU, so I didn't use it. But if you have multiple GPUs, you can speed up the training this way. And people who have Macs, for example, can use a device argument to specify that they would like to use MPS, so the Apple Silicon, rather than the regular CPU for the training or deployment. And probably the last one on that list that I think is really interesting is the patience. So patience is the parameter that you can use to stop the training. So the model is actually constantly evaluated during the training, and we can use the patience to stop the training if we see no progress during the training. So if, for example, for 10 epochs, the accuracy of the model did not improve, there is a high chance that it won't improve in the next 50 epochs. So we might just as well decide to stop the training right now and save some time and save the money that we would use for the training. As you can see, there are a lot of other parameters that you can choose during the training. So I highly encourage you to go through that list, look for something that sounds interesting, try different values, and experiment. Okay, we are back in terminal and we can see that our training is almost done. We are just performing the final evaluation of the model and it's completed. And we can see that results of the training have been saved to runs detect train to directory. So let's run ls-la on our current directory and we see two things happened. First of all, YOLO11n.pt file was saved. This is the checkpoint that we used to initiate the training, and it was just cached locally so that if we would rerun our training job, we wouldn't need to download it once again. But also, there is a new directory created called runs. And this is the directory that is created by Ultralytics CLI during the training. And if we will run 3-D on this directory, we'll see that inside we have detect subdirectory, and inside the detect directory see another train and train2 directories. So why do we have two train directories? It's because our first training job actually failed. Remember, we did run YOLO detect train command, but it failed because it couldn't locate all images from validation set. But because it did run, the train directory was created. And then when we rerun the command to train the model once again, another train2 directory was created. So if we would, I don't know, update the hyperparameter and run the train job once again, another train3 directory would be created. And we have this detect directory because we did run detection task. If we would run another training job, but for segmentation, we would have detect and segment subdirectories in the runs directory. Now, let me open runs detect train2 directory so we can examine the artifacts that were saved there during and after the training. So the first thing that we see is the weights directory, the first one from the left. And inside, there are last PT and best PT files. Those are the weights that were saved during and after the training. But we'll play with them in just a second. For now, let's focus on other assets that are in this directory. And the first thing that I want to take a look is the confusion matrix. So this is the chart that helps us to understand how many false positives and false negatives happened during the model evaluation after the training, but also whether the model confuses classes. So whether the model detects the object but fails to assign the correct class to it. And from this chart, we see that the model has pretty much only one weakness, and this is false predictions of text class. That means that the object detects text where there shouldn't be any text. And that's probably related to a short training time. So if we would have maybe 10 epochs instead of 5, we would be able to optimize the model in this specific edge case. Another interesting artifact is results.png. So, like I told you, during the training, the model is constantly being evaluated, and we use multiple different metrics to do that. And on this chart, we see values of all of those metrics after every epoch. And we can see that at epoch number 5, box loss for train was still higher than box loss for validation. That means that our model is most likely under-trained, and we could easily train it for 10, 20 epochs longer, and it would still be not overfitting. And the last thing that I would like to take a look is val batch results. So those are bounding boxes representing detections that happen during the evaluation of the model at the end of the training on the validation set. And here I mostly look for things that are clearly wrong, something that I can visibly see, and maybe do some adjustments in my training set to improve on those specific edge cases. But here on this chart, I don't see anything clearly out of ordinary. We finished the training, we evaluated the model, now it's time to put it through the test. Since we trained the model capable of analyzing research articles, let's use it to process some ML papers. It would be awesome to use it to process a paper talking about YOLO11, but traditionally Ultralytics did not release a paper along with the model, so I got creative and picked another iconic paper for us to use. Let's check how our model handles detecting text, tables, and images in Attention is All You Need paper. Okay, so I did found Attention is All You Need paper on the internet. It's in PDF format. So let's download it to our downloads directory. And once we do it, let's go back to the terminal. And first thing first, let's confirm that it is really in the downloads directory. So let's do ls-la on downloads, and this time grep for PDF files. And yep, there is only one PDF over there. That must be our Attention is All You Need paper. So now let's copy the paper from downloads into the datasets directory that we created at the beginning of the tutorial. And inside datasets, let's create test directory. What I will do now is I will convert that PDF into range of PNG images, and I will save them into this test directory. And to do it, I will use a little bit of image magic. So image magic is a command line tool, is a package that helps you to do crazy things with images. And it's not really related to the topic of this tutorial, but the command that you see right now on the screen will help us to convert that PDF file into a list of PNG images, and we'll save that to our test directory. We'll do a lot of things along the way, like removing the alpha channel and setting the background color to white. And once that will happen, we will run the inference on those images. If you are interested in Image Magic, I highly encourage you to visit their GitHub page. The docs are crazy, so it's not easy to learn that tool, but it's very powerful. Now, let's take a look at the images that we generated. So let's open that directory in the UI, and we see that we have separate PNG file for every page. And we can see this iconic transformers diagram on the page 3. Okay, so now we can go back to terminal and run detection through the CLI. So once again, we do a YOLO detect, but this time we set the mode to predict. We specify few arguments. The first one is source, and here we pass the path to our test directory. This way we say that we want to run the inference on every asset that is in that directory, so on every image. And we also specify the model that we would like to use. In our case, we will use the best model we got from our training job. So we do runs detect train to weights best PT. And then when we run it, we see that the CLI shows us what classes and how many instances of every class were detected on every image. And we also get an information that the results were safe in runs detect predict directory. Now you can just copy that path and open it in the UI to take a look. We can open the first image from the left. This is the title page. It is a little bit unfortunate that Ultralytics decided to use white or almost white color to represent this class, but you can still see that sections of the text were correctly detected. Take a look on another page. And yeah, we managed to detect this iconic transformers diagram on page 3. Looks like it works. Now let's switch the environment and let me show you how to run the training and evaluate the model in Google Colab. As usual, the notebook for this tutorial can be found in RoboFlow Notebooks repository, where we store demo notebooks for all our YouTube tutorials. The link to the Google Colab for this notebook will be also included in the description below the video. Here we just need to scroll a little bit lower to model tutorials table and look for YOLO11 object detection, then click open in Colab button. Once we do it, we'll get redirected to Google Colab, And before we start the training, we need to take care of few setup steps. The first one is to add RoboFlow API key to the secret step. So to get RoboFlow API key, you need to sign in into your RoboFlow profile, or of course create one if you don't have it yet, and then go to Settings, API Keys, and here we copy the private API key. Once we are back to Google Colab, we open the Secrets tab that is in the left side panel of Google Colab, and we add new secret, call it RoboFlow API key, without spaces, with underscores, and all capital letters, and enable the access to that specific secret so that we will be able to use it later on. Now, of course, I have my API key set already, so I'm just closing this tab. And the next step is to confirm that we have access to the GPU. And similarly to the local training, to do it, I run NVIDIA SMI. And here, what we can see is the version of the CUDA that is accessible in this environment. If you don't see similar output, maybe with different CUDA version or different GPU, what you need to do is you need to open runtime, then click change runtime type, and most likely you are on the CPU version of Google Colab, so you need to choose one of the accessible GPUs. I'm using NVIDIA L4, but I'm pretty sure it's not accessible on the free tier. So if you are on the free tier, just choose T4 GPU, click save and restart the notebook. If you set your secrets, they should be still there. So it's only to get the access to the GPU. The next step is to install the required dependencies. So on a local, before we installed Ultralytics, we need to install PyTorch, and we needed to make sure that the PyTorch version is right for our CUDA. Over here in Colab, the PyTorch is already installed, so we don't need to install it. What we can do is run pip list and grep to look for PyTorch, and we see that both Torch and Torch Vision are installed, and in both cases they're installed with the CUDA support. So that's perfect. All we need to do is run install Ultralytics and install RoboFlow, because here we will use Ultralytics to run the training, but we'll use RoboFlow to pull the dataset from RoboFlow Universe. So far, we only downloaded the dataset as a zip file. Let me show you how to do it using RoboFlow SDK. So just like before, we select Dataset in the left side panel, but this time when we click Download the Dataset button and select the appropriate export format, we will select Show Download Code instead of Download Zip to Computer. And once we do it and click Continue, the code snippet will get generated. I'll just copy the last 3 lines of that code snippet, but if you want the code snippet that will install RoboFlow SDK, give you your API key, and download the dataset all at once, you can just copy that, paste it in the Colab and execute. I will just go back to Colab and update those last 3 lines of that code snippet, execute the cell, and downloading of the whole dataset will take a little bit of time. As a matter of fact, according to what we see on the screen, it will take around 3 minutes. So let's use the magic of Cinema to speed up the whole process. Okay. Our dataset is downloaded, so now we can open the file browser in the left side panel and take a look at its structure. We did that already for a local training, so this time I will go very quickly and only talk about the most important things. So the dataset have 3 subdirectories, test, train, and valid, and a data YAML file that provides the most important metadata about the dataset. At the very top of the YAML file, we have 3 keys, test, train, and valid. Those store relative paths to images directories that are located within each subdirectory. So now if we open those subdirectories, we see that each of them have images and labels directories inside. And if we open one of those labels directories and click on one of those txt files, we see a typical YOLO annotation format. We spoke a lot about that format in the section covering local training. So if you're interested, feel free to use the chapters. You will learn a lot more. Our environment is configured, our dataset is downloaded, so we can start the training. But before we do that, let's open the Resources tab that is on the right side of Google Colab. We'll use it to keep track of the GPU VRAM usage during the training. And by the way, over here we see that the total amount of VRAM that we have at our disposal is 22.5 gigabytes. So it's actually a fairly large GPU. And like I said, if you are on a free tier, you wouldn't have access to it. But I use it to experiment a little bit. So contrary to what I did on a local, here I will train the same model, but twice as long when it comes to epochs, but probably faster when it comes to time, as I will set epochs to 10, but batch size to 128. And I can do it because it's a fairly large GPU. Now I just hit enter and start training. Just like on local, we see the list of all parameters along with values, the definition of the neural network, and when we scroll lower, we see that our train and validation sets are being loaded. And the training should start in just a matter of a few seconds. And once the training starts, we'll see a drastic spike on the GPU VRAM usage chart. So the first epoch have just started, and the spike should happen right now. Exactly. So we see that immediately we allocated 17.4 gigabytes of that VRAM, and the single epoch takes around 1 minute to complete, and we will run 10 of them. So let's use the magic of Cinema once again to speed up the process. The training have completed, and we see that the artifacts were saved in runs detect train directory. So now let's use Linux ls command to list all the files that we can find there and display few charts that will tell us a little bit more about the quality of the model that we trained. So the first chart that I'm interested in is the confusion matrix. So if you saw our local training, we had a small problem with the model that we trained locally. It had pretty much one weakness, and those were false positive for text class. And back then, after 5 epochs of training, we had over 500, maybe even 600 of those false positive on the validation set. And here we see that with just changing the epochs count from 5 to 10, we managed to lower that value below 400. So the model is significantly better at not producing those false detections. The next chart that I'm interested in is the results PNG. one where we have the values of all the important metrics that were collected during the training. Here, the most important metrics is box loss, both for train and validation set. And we can see that the box loss for train is still higher than the box loss for validation. So you can see that the model is still not overfitting. You could still probably train it for a little bit longer, and it will probably produce even better results. And the final thing that I always like to take a look at is a subset of predictions from the validation batch. Just as a sanity check to look for anything that is clearly out of ordinary, but similarly to the local training, I don't see any problems with this model. And as a final step, we'll run our CLI in validation mode. So what will happen is we'll load our freshly trained model into the memory, and we'll run it against images from the validation set to compute the MAP5095 metric for each class and for all classes collectively. This is the most popular metric to benchmark object detection models. And we can see that in all cases we crossed 90%. This means that at least on images from the validation set, the model is handling that very well, and it's capable of detecting images, text, and tables with high accuracy. We know that our model works well, so now it's time to save it. This is especially important if you run your training in Google Colab, because Google Colab environment is only active for several hours, and once that time passes, all files that were accessible in that environment will be deleted, including your freshly trained model. So, of course, you can download that file to your local. That works especially if you have only one project that you plan to work on. But if you have multiple projects, I guarantee in 3 months' time, you will not remember what have you done and in what project. So I actually recommend you upload the weights to RoboFlow. And let me show you how to do it. So I'm not sure if you remember, but we actually trained the model on the dataset I found on RoboFlow Universe. So before we'll be able to upload our weights, we need to fork that dataset so that it will be assigned to my account, and then I will be able to tie my new model to that dataset. To do it, I go into Images and click For Dataset Beta button. And once that happens, the forking process is triggered. Depending on the size of a dataset, it may take more or less time, but my dataset is fairly large, so it will take a little bit of time. But once that process is completed, we'll end up in this view. So this is now my dataset. I can, for example, change the name of the classes here. I can upload more data. I can annotate more data. So that gives me a lot of options, especially if I would like to improve the model that I just trained. But importantly, it allows me to upload my newly trained model into this project. So let's do it. At the bottom of the Google Colab, you will find a code snippet that shows you how to upload the weights to RoboFlow Universe. But that code snippet assumes that you are the owner of the project that you used for training. And in our case, that is not the case. I use the project from RoboFlow Universe, and I just created the fork, and I would like to tie the model to that fork. So to do it, I will just paste this code here. This way we'll use RoboFlow SDK to load the metadata of our fork. And now we'll just make small updates in the code snippet, switch the version to our project, and run the cell. Now the weights are being uploaded into my fork. I can click this link that is displayed, and this will take me to the page where the model will be loaded. Depending on the size of the model you uploaded, that might take a few minutes to complete. But once it's completed, this view changed into something like this. And now we have a lot more options. First of all, we have all the metadata of our training, but we can deploy the model in all different ways. Let me show you how it works. I will just take one page from Attention is All You Need paper, and we'll drop it here. And immediately the model will get loaded into the memory of the browser, because it will run locally. I'll run Inference on that file, and we can see that just as in the case of local, the model is capable of detecting both the figure and the text on that page. Awesome. Don't get me wrong, running your model locally in browser is cool, but uploading your weights to RoboFlow allow you to do so much more. Depending on the use case that you're trying to solve, whether or not you train the model to detect animals or parts that are manufactured in the factory, you can, for example, deploy that model on small edge device like this, Jetson Nano, and run your inference directly in the forest or in the factory to lower the inference cost and the latency. You can, for example, deploy it on phones or in the cloud, or you can deploy your model in Colab, and that's exactly what I will show you right now. And we are back in Google Colab. I know, long time no see, but this is actually a new Google Colab, separate environment. I created this so you can be sure that the weights are no longer here. The weights are actually in RoboFlow universe, and we'll pull them. To do that, we start by installing two Python packages that we are going to use. The first one is Inference, that we are going to use to pull the model and run it locally. The second one is Supervision, that we are going to use to visualize the result of our inference. Once the dependencies are installed, we need to make sure that we will have access to RoboFlow API key. This is the same key we used before to pull the dataset from RoboFlow universe or to upload our weights, and now we'll use it to pull our model back into fresh Google Colab environment. I will copy that code and close the tab, paste it here. And now we'll use Google Colab SDK to extract the value of RoboFlow API key from secrets into the constant. So to do it, we'll call user data get and pass the name of secret we would like to extract. In our case, it's RoboFlow API key, all capital with underscores instead of spaces. Now it's time to pull the actual model. To do it, we will use a get model function that we need to import from Inference package. And to pull the model, we need the API key, but we also need model ID. And we will get that model ID from RoboFlow UI, from the page that was created when we uploaded the model. Okay, so we just copy this string and go back to Google Colab, paste it as model ID, and now we are ready to load the model. So I just create a new variable, call it the model, and call get model function, pass model ID and RoboFlow API key, hit enter, and after a few seconds the model should be loaded. And now what we can do is we can test the model on some example image, and I'm just lazy, so at this point I will just upload the third page from Attention is All You Need paper so that it will be accessible in Google Colab environment, and we will just use OpenCV to load that page as the NumPy array. So let's do it. So first thing first, I import OpenCV. So we type import CV2, and now I will define a new constant, image path, copy the path to our uploaded image, paste it here, and create a new variable called image, run imRead function from OpenCV, pass our image path, hit Shift Enter, and now the image is loaded into the memory. The next step is to run the inference. So I create the results variable, run model infer function, pass the image along with the confidence level. Let's set it to 0.4. And that would return a list by default. So I just pick the first value from that list. Here is the results object that we got. So now we will use the supervision to parse that result and display the bounding boxes on the image. So we import supervision as SV, and we SV. And now we will create a detection object from that inference result. So we create variable called detections, call sv.detections from inference. And now we will pass our results object into that function. And as a result, we'll get the detections object. So the results object and the detections object store the same information. It's just detections is the object that we can use to pass to all sorts of different utilities that we have in supervision. Next, I always like to create a copy of the original image before I annotate anything on that image, in case I will mess something up. And first thing first, I will run a box annotator to draw bounding boxes around the detected objects. I just pass the annotated image and the detections. Now you can copy all this, paste it below, and now change the box annotator into label annotator. Run that cell. And right now the annotated image should have both the boxes and the labels, so we can display that image in the Google Colab. And yeah, there you have it. We have all the detected objects, just like in the UI, just like on local, model works. And that's it. I really hope that you enjoyed the video. It turned out to be quite a long one, but we covered a lot of useful things like how do you annotate the data, or what is the data format for YOLO models, and how to train the model in 2 different environments, and of course, how to deploy the model in the end. I think that's a very solid foundation to anybody who would like to use YOLO11 in their project. So if you enjoyed the video, make sure to like and subscribe. If you have any questions, leave them in the comments. My name is Peter, and I see you next time. Bye.